Get started again. Princeton has two environmental research related institutes. One is the Analytics Center, the other is HMEI, High Meadows Environmental Institute. So today we are fortunate to bring the director of HMEI to come us and help us to moderate one of the very exciting session is AI for climate. Without too much delay, I'll pass it to Professor Gabriel Vecchi.
All right, thank you. I'm just going to offer a couple introductory thoughts and then get to the panelists who really are what we're here for. So Princeton has been at the forefront of sort of transformative technologies for understanding climate. Suki Manabe was one of the awardees of the Nobel Prize for Physics for his sort of leadership role in developing climate modeling here at Geophysical Fluid Dynamics Laboratory in Princeton University. And that was a tool that was based on physical understanding, right? So this is an idea that goes back to the 1920s, the Richardson's idea for a numerical weather prediction system that used physics. Although in the 1920s, when Richardson had this idea, he did not have the technology, the applied mathematics, the computer sciences necessary to actually implement the idea. And following the development of computers in the 1940s and 50s, eventually we were able to take this idea and turn it into reality. That was a way to take our understanding of physics and make predictions of the state of the climate system, of weather, of different environmental parameters. And it has been resulted in a series of very useful tools that have enabled not just practical prediction, yes, hurricane forecasts, the seasonal forecast of El Nino, projections of climate change, but also has enabled our ability to understand the underlying system, the underlying climate system better, and allowed us to design observing systems, sort of to just push our understanding forward, right? And it was a practical tool that had the dual purpose or the multiple purpose of understanding and practical application. Simultaneously, there had always been this effort to try to use the data that we had about the system to also build predictions, statistically based predictions of the climate system using analogs, using regression techniques, using some machine learning or AI methods such as sort of principal components or other things, sort of in a relatively unsophisticated way, although sophisticated for the time, but now would be deemed unsophisticated. And they carried a lot of promise, but the realized sort of utility was not demonstrated. Over the last few years, we've had some really tempting results coming out of largely the private sector, making some interesting claims about weather prediction using AI and machine learning. I think that some of that remains to be really tested in a rigorous way. But I think here at Princeton, we can still play a leadership role in actually building this robust set of tools that results both in practical utility and in predictive understanding. So we have our panelists here, and I'll invite them in order to make some introductory remarks, and then we'll go to a moderated discussion and Q&A. So first, I'll introduce the three. We have Adji Bousso Dieng, who's a professor in computer sciences, and then we have Reed Maxwell, professor in civil and environmental engineering and at the High Meadows Environmental Institute, and then Ning Lin, who's a professor in civil and environmental engineering. And so with that, Adji, if you could give your remarks.
Hi, everyone. Thanks for the introduction, Gabe. I'm happy to be here. My name is Adji Bousso Dieng. I'm an assistant professor in the computer science department, where I lead the lab Vertex on research at the intersection of AI and the natural sciences. Our approach is really to develop methods around fundamental concepts that underpin many problems in the sciences, and then use now those methods to go back to the sciences and solve the problems. So sometimes what we do has nothing to do with AI. One concept, for example, that we have worked on that underpins many scientific problems is diversity, that not many scientific fields have been working on, except for ecologists. They center diversity a lot. So we've been working on that concept because it's behind many failure modes of AI, for example. These generative models, they tend to only capture certain aspects of your data and miss other important aspects of your data. So that's a problem, including in climate, if you want to use these models to do forecasting and things like that. Diversity is also underpinning the problem that happens in simulations, molecular simulations, where the scientists, they run the molecular simulation and it gets stuck in one area and you cannot really capture all the different these called configurations, conformations of your molecular material in order to understand its properties. In search as well, when you're searching these large, high-dimensional spaces, you want to be able to be diverse in your search so that you can explore different areas of the space. I mentioned these examples because they are relevant when searching for materials, which is one approach to the climate, AI for climate, that not a lot of people have been looking at. There's been a lot of work on AI for weather forecasting. There's been a lot of work on AI for extreme event prediction. There's been a lot of work in hybrid modeling, where you use climate models and machine learning in order to make more accurate predictions. And there's been less on developing materials that are using AI that are sustainable, that allows us to build more sustainably, or materials that allow us to do things like capture carbon dioxide, capture ammonia, which recently I've learned is very relevant to the environmental problem, or capture toxicities that we have in our environmental spaces like the ocean and things like that. And so my lab has been working also in leveraging this diversity concept and the methods we build around it to make discovering materials with targeted properties easier. So for example, we've used a search method that uses diversity to find metal organic frameworks. These are a class of materials that can capture CO2, capture ammonia, and do things like that, because they have these pores in them that actually serve as a way to store things you want them to store, CO2 being one of that, NH3, ammonia being one of that. So we've worked recently on a method that does that. And we actually were able to find, among those materials, one that's beating the one that's deployed in the market right now when it comes to ammonia. And we're looking at how to actually synthesize it. I'm not saying that to say that there's not been AI for materials in the field, but the advances in AI for materials that we've seen so far is more like a general, like these general approaches that try to discover as many materials as possible. They are not specifically focused on climate and environment and sustainability. And there's less regard on synthesizability, which is very important. You don't want to just show that you can discover materials. They have to actually be things you can make in the lab and that are stable and that have the properties you actually want. So if you care about climate and sustainability for a specific climate sustainability application, you want to be able to have these algorithms, AI for materials, to be able to actually lend you to something that has those properties. So we've been working on that. Other things we've been working on related to diversity is in evaluating generative models better. For example, we have an upcoming work that has shown that these generative models, they tend to memorize data points that contribute least to diversity, and they tend to fail on data points that contribute most to diversity. Data points that contribute most to diversity in climate or the environment or sustainability are rare events. If these models are actually failing in predicting or generating these events, is that they're actually, at the moment, not adapted to solving climate and environmental issues. And there's been a lot of work in that space, in leveraging AI to do all these things. But I think there are still pending challenges. One such challenge being uncertainty quantification. I think that was mentioned in the previous panel. AI systems are typically based on these deep learning methods that don't care much about quantifying uncertainty. And if we were to go about quantifying uncertainty using these neural networks, the typical way to go is to build these Bayesian neural networks. And at the scale at which these models are, which is that they're very large, Bayesian deep learning becomes very challenging to do. It becomes very hard to do posterior inference on these models. Another challenge that's pending is the ability to have dynamical systems that can impute accurately. And that's important because the current models we have are very coarse. You want to be able to impute at a finer grain by just leveraging coarser models. So that's one challenge that's pending as well. We want to be able to have systems that can capture the different scales that are reflected in these processes. There are phenomena that happen at the small scale that you want to be able to capture, and also capture phenomena at more coarser scales. So you want to have a model that can mix those different scales in interesting ways, so that you can predict more accurately. So that you can do prediction more accurately. And finally, one thing that we're missing, of course, is that because climate pertains to so many things, we need to be able to involve many different communities and many different scientists from different domains, ranging from ecologists, climate scientists, to policy analysts, and also material scientists, in order to really tackle challenges that climate poses. I think that's all I had to say as an introductory remark. I'll wait for the questions from Gabe and the audience. Thank you.
Thank you so much. Thanks, everybody, for hanging out to the bitter end. And thanks, everybody, for all the great panels today. I've been in and out most of the day, but it's been super exciting discussion. And thanks, Gabe and others, for inviting me. So my name's Reed Maxwell. And as Gabe mentioned, I'm in Civil and Environmental Engineering and the High Meadows Environmental Institute. And I also direct a center here on water. And I'm going to talk a little bit about some work that I've done integrating AI data and community platforms. But first, I kind of want to set the stage for all of what we're doing here, and that's that water is becoming a thing. And what I mean by that is I've been in the water business, so to speak, for about 25 years, and there would never be a New York Times headline about depletion of groundwater or about PFAS or about any of the things that we study here 25 years ago. And some of that is because our water problems are getting worse, and some of that is that our federal agencies are getting better at communicating these risks. So this is a product that's put out by NOAA. I love this. I use this infographic a lot. This is the 2023 $1 billion weather and climate disasters. Each of these icons is a weather or climate-related disaster that caused in excess of $1 billion in damages. And you just sort of look across the board. There's floods, there's droughts, there's tropical cyclones, there's all manner, there's tornadoes, there's all manner of things that, as Gabe really nicely introduced, that we study here at Princeton. And if we look at the costs associated with this, and as I said, I've been using this for a long time, and I used to do a 3-year running average. Now I just do each year because last year alone, we lost $600 billion, more than $500 billion due to weather and climate-related disasters. And so just to sort of set the stage for a lot of the things that we'll talk about and a lot of the things that we work on here. Now, in my own work, I do a lot to build these really large-scale hydrologic models that include groundwater, surface water, plant interactions. We call them sort of bedrock to the top of the atmosphere. This is a paper that we published a little while ago on one of our modeling simulations. And this work shows amazing promise in doing things like projecting climate change impacts to the water cycle at continental scale at really high resolution. And these so-called integrated models do an amazing job of this. But this particular simulation was 16 water years of total simulation across all the scenarios and time dependent. And each water year takes 500,000 CPU hours. And so this paper, this simulation was 8 million CPU hours total, which is this giant leadership scale type exercise, and got us a paper in Nature Communications, but is completely impractical for use for water managers, for decision makers. And so this is where AI comes into the picture. And if we look at this, one of these two images, these are both water table depth over a watershed that we have studied a lot. One of these is an imposter. So one of these is a Turing test. One of these is an AI, and one of these is the real model. So how many of you, we'll do a raise of hands, how many of you think that figure A is the real model? How many of you think that figure B is the real model? Well, it's low, it's late in the day, but not many people voted. All right, Gabe, you were right. Figure B is the real model. But statistically, they're identical, right? It's almost impossible to tell the difference between these two. Now, the whole difference is we can do this now at continental scale. So this is the same thing. This is our simulation, same simulation that took 8 million CPU hours. This is our emulator simulation. It's 1,000 times faster. So this simulation runs in about 90 minutes on a single GPU, whereas the prior simulation ran on roughly 4,000 cores of a leadership computer, supercomputer, in about 40 hours of wall clock time. And so this is really a transformational speed up and an ability to completely revolutionize how we do and what we do. Now, of course, we need a lot of data. We work on real problems. They have real answers. They're real places. We make real predictions. So in addition to accelerating the simulation, we've also constructed these really big databases. In fact, we have the largest database, largest hydrologic database for the US. So we've cloned and continuously update databases from several different federal agencies that and provide one unified API. This all sits on a Princeton data center, which sits across the street at the Forrestal campus in the machine room, and is free and open to the public. And we combine data sets from the USGS, from USDA, from NOAA, National Weather Service, and we provide a really easy way to access these data across different agencies, all of which have different mandates and different missions and can't sort of cross-populate each other's data sets. And then also, this allows us to do data-driven machine learning in a way that was not prior possible. And this, for example, this is some work that came out of my group. This is a data-driven water table depth product at 30-meter resolution, or 1 arcsecond, over the entire continental US. And this represents our best estimate, statistically, this is our best estimate of the water table over the continental US. And because the water table is, groundwater is most of our freshwater storage, this is actually the best estimate we have of how much freshwater we have in the continental US. And this has led to really exciting new stuff. So this is a brand new project that just kicked off a couple weeks ago. This is the National Science Foundation NAIR, or National AI Regional Research Resource Project. And we, along with colleagues at the University of Arizona, are one of the pilots. And we're building a digital twin for the hydrology, bedrock to the top of the atmosphere of the entire continental US. And as we move forward, we really need to think globally, because while we have big water challenges in the US and we have lots of data, our water challenges are small compared to the global south. And we really hope to think about how we connect with the rest of the world and how we build collaborations and partnerships. And so we've already started this. We have continental West Africa simulation models. We have continental China. And what we're really doing is building partnerships. And this is very much like other global communities, right? The climate community has been doing this for a really long time successfully. And the hydrology community and groundwater community is just kind of catching up. And through building these research partnerships and connecting with local scientists and stakeholders, we really provide ownership in these models and simulations and data. So I think it's super exciting. Thanks again for your attention. And I think we're in this revolution of data and simulation, and I think Gabe, really pitched it nicely, talking about how, we've been and still are very physics-based and have a deep understanding of the physical processes. But we also are in this, revolution of data, and so we really want to bridge this divide. So with that, thank you very much. I will hand it off to Ning, and I appreciate your attention.
Thanks, everyone, and thanks for setting the stage. So I'm going to talk about physics-based machine learning approaches that we tried in hurricane projection and risk management in a changing climate. Okay. Can you hear me better? Can you hear me now? Okay. Thanks again, everyone. So I'm going to talk about physics-based machine learning approaches in hurricane hazard projection and also risk management considering climate change. So Reid has talked about impact of hurricanes, or generally called tropical cyclones, among other natural hazards. Here are just additional data points on the impact. And the lower figure shows the United States losses from tropical cyclones. And we can see that in this year, we have Hurricane Helene, and Milton will be added, a big spike here in 2024. So we can see that the increase of the potential, the damage and the losses and the impact has been increasing over the past decades, mainly driven by the coastal development, but also due to climate change. And both trends will continue in the future. So to understand the future hurricane risk and impact and mitigate this risk, we work on this physics-based TC hazards and risk management framework, where we will model the tropical cyclones, or TCs, from global climate models. And then we model the hazards from these TCs, including wind, storm, surge, and rainfall. We also consider other compounding hazards, including sea level rise and heat waves. And on the other hand, we model the natural and built environment vulnerabilities. And combining hazards information and vulnerability information, we can quantify the risk to support risk management. So I see AI is applied in all these elements. So I will talk about a few elements today. So first I'll talk about, we model the TCs, or the storms. So we developed Princeton environment-dependent probabilistic tropical cyclone model called PAPC, where essentially we use machine learning methods to develop statistical relationship between climate environment related to TC development and the TC characteristics. So specifically, we model the TC genesis, or the initialization of TCs, as a dependent spatial temporal Poisson process on clustering grids based on similarity of the environmental variables relevant to the genesis. So for example, those would be the simulated TC initial locations compared to the observation. It's not perfect because this is built on very limited data sets, but it's improved over previous simple statistical methods. And then we model the TC track, use analog wind TC track model. So this is to model the track based on the pattern of the historical TC track and also the environmental wind. And this is observed tracks, and those are the simulated tracks samples. You can see that the simulated tracks can mimic the observed track, including this recurving at the high latitudes. And for the intensity of the storm, we model them as using a dependent hidden Markov process. So the intensity is dependent on the climate environmental conditions. So on the left, this is observed intensity on the historical tracks. And on the right, this is intensity on the simulated cases. So they can look similar. And at the same time, we can look at the distribution of the intensity over the basin. So this is a distribution of the lifetime maximum intensity. So we can capture the distribution for the general storms, but we can also capture the distribution for so-called rapid intensification storms, including Hurricane Helene and Hurricane Milton. So those will be possible only using a more advanced machine learning method compared to the previous simple regression. And so put all these elements together, we can simulate a large number of synthetic storms over the whole basin, and we can look at the impact at a landfall. So we look at landfall at different regions of the United States, and we look at the landfall intensity as a function of return period for different regions. So the black is a 36-year observation, and the red is 36-year simulation for the whole basin. They compare very well. But now we can use this model to simulate a much longer time period to look at the extremes that's beyond the historical observation. And we can use this model to downscale the global climate model, the newest climate model, CIMES 6. So this is a frequency of the storm over the Atlantic basin predicted by each of the climate models, and the black is the average of them. You can see that the model actually predicts that the storm frequency will decrease over the basin due to climate change, which is consistent with many other models. But at the same time, model predicts that the distribution of the intensity will be moving to higher values over time. So that means the frequency of intense storms will increase in the future, and those are the ones that are causing the large damages. So this is about the modeling of the storm. We can also use AI to model the hazards associated with the storms. Here we have a physical model, hydrodynamic models to simulate storm surge. We can simulate it for the whole basin scale, or we can simulate the storm surge at very high resolution at the local scale. Those are the simulation comparison between measurements of storm surge and also simulation. So we can get quite good results if you put a lot of computational efforts. So this is very computational intensive. So we try the AI method simply to start. We use a neural network to model the storm surge based on the physically simulated data sets. And then we model the storm surge as a function of just the storm parameters at landfall, including the track, intensity, and size. And here are some results showing at different locations we can get the prediction based on the neural network compared to the physically based storm surge relatively well. We can use more advanced models, and more training data can even improve these results. For rainfall, we can also simulate rainfall using AI methods. Here we first use the physics-based model to simulate large number of images of the rainfall from tropical cyclones. We also use satellite observation to train the model. And then given this trained model, we can compare with simulations. This is a physical model simulation for different tropical cyclones, and those are the samples from the simulation of the machine learning method. You can see that many cases we can capture the spatial pattern quite well, except the Hurricane Sandy, which was a very difficult storm to model. In addition to model the storms and the storm hazards, we can also think about AI application in risk management or decision making. So especially climate projection is very uncertain. So we think that we have to incorporate learning and updating in our systematic decision making. So here is a machine learning application again. So for example, after Hurricane Sandy, New York City has been discussing about protecting Lower Manhattan. So the basic idea is we can build a wall around the Lower Manhattan with a fixed height. But we think that because the climate change is dynamic and is very uncertain, we can develop dynamic approaches. For example, we can use dynamic programming to design the seawall that increase over time. Or we can use Bayesian learning. Every 10 years, we can check sea level rise and confine our uncertainty. Or better, we can use reinforcement learning. That means we can make our decision now based on observation, but also based on our understanding that in the future, we're going to observe the sea level rise and make adjustments on our strategies. So we apply this approach to the seawall problem for different two emission scenarios. So the green curve is a design from the current design, big U, so it's a constant wall over time. Or we can use static optimization, another constant wall. Or we can use dynamic programming in blue, or we can use reinforcement learning, which is this shaded for the probability density function for the wall height, because it depends on the future observation. And comparing about the total cost, including expected future losses, the reinforcement learning will save a lot of money compared to previous methods, especially for the current big U design in New York City, especially for the high emission scenario. So just some examples about various applications in such a framework for assessing TC hazard risk. So my graduate students take all the courses in machine learning and trying to figure out the application of that in their research topic here. Thank you.
All right. So thoughts based on this and thinking about some of the challenges ahead of us, both locally, thinking about sort of the academic challenges of how do you do this, and then thinking about globally the academic, the non-academic questions of how do we live in a changing environment where our decisions affect our challenges, right? So, Adji, you mentioned working on materials that would help us perhaps mitigate some climate changes by maybe capturing carbon or ammonia or other greenhouse gases. I think with Ning and Reed, we saw some potential to use better information to make decisions about water and extreme events. So what do you see as, sort of academically, the type of structures that we should be thinking of setting up so that we can educate the leaders of the future in this, and are they in place right now? And then thinking in a larger sense of applying these tools, what do you see as structures that would help us better integrate the different approaches, integrate them with thinking about energy, as a way to better apply these to the practical questions at hand? I don't know if you want to take them in turn or take them, so how can we be a better educational and research institution and contribute to these solutions? And then how can this be applied? And anybody that wants to jump in can jump in.
I mean, this is a big question. And from my group perspective, I think the students have been taking the initiative to take courses in machine learning. And I guess the big thing for us is to remind them about taking advantage of physical understanding and the big data and the techniques in machine learning together, rather than diving to data-driven and reduce their emphasis on the physical understanding or the other way. So that's...
I'll augment Ning's great answer, and it's a big picture question, Gabe. Thanks for throwing us a softball off the bat. No, but a really important question, right? So I think that the physics and understanding, particularly as engineers and as scientists, can't be replaced by the machine learning, by AI, by just the data. And that it's interesting to see sometimes when there are things explained by the data that are at odds with the physics understanding. But I think you can never understand that, and you can never do this. You can never cross-check what the data provides or the data says by itself if you don't have a physical understanding. And so I think that's a real challenge, because the knee-jerk answer is that students should just take double the classes, right? They should still take all the physics classes they took, and they should take machine learning and data science, and they should, and that's maybe not the right answer. I think we want to rethink this in a little more holistic way. But I think right now what happens is, the students are the integrator between, say, different faculty or different perspectives, and are used in a way to expand and be more multidisciplinary.
I would agree with the multidisciplinary aspect. That's a reflection to the research we do in the lab. And one approach would be to show limitation of only using one approach. The data-only approach, if you assumed that you observed all data that is to be observed, you can train a neural network and replicate behavior. But the problem is that we don't observe all the data we want to observe. So there's limitation there. On the physical side, relying only on physical models, sometimes these are intractable. I'm taking example of, for example, systems that are described by partial differential equations. Sometimes they're intractable, and you want to resort to models that can actually allow you to find solutions to these. And people have shown that actually neural networks can help with that. So that's to illustrate that I think the hybrid approach of modeling a system by relying on both the physics and observations seems like to be an optimal way to go. And any educational program that aims to make students more aware of challenges in climate, I think should give them the skills they need on both AI and the physics. And also why it's important to study climate, just as a reminder. And having them have this global view that it touches every part of the planet, and that doing well in every part of the planet in terms of predictions is good for everyone. Yeah.
Okay. So when we have these new technologies, right, and I'm going to treat AI and ML as a new technology, even though it's been conceptually there for quite a long time, but the computers and everything, the algorithms are now there so that they're relatively easy to use. One of the temptations is to use them to do the same thing we've been doing better. Another temptation is to do altogether different things than we have been doing. And then there's, of course, intermediate solutions, right? What do you see as a relatively, if not low-hanging fruit, a straightforward target for a way to do something that we've been doing now for decades better? And what is something that you see as an ability to do something altogether new that was essentially inconceivable without access to these data-driven approaches? We can go now in the opposite order. So starting with Adji.
Yeah, okay. I think the idea of imputation is something we can do better now. There are these coarse-grained models that may lack the ability to give you fine-grained resolution when you're dealing with AI systems. And people have been developing these dynamical models like Mambas, for example, or alternators that are very good at imputing missing data. And I think that's something that we can do better now. Yeah.
So I'll give an example. In hydrology, classically for flood forecasting, which drove a big component of hydrology and has been really successful, in saving lives and prediction, relatively simple models are used. And the idea was you take a very, pretty simple conceptual model, a lot of data, you spend a lot of time calibrating the model for different regions, different circumstances. And then when AI kind of ML and particularly LSTMs, so long short-term memory and other recursive type models came in, their use was exactly the same. So you could just think about the process was exactly the same. So it was exactly as you said, right? So it was just like, oh, we can just trade out this model with an LSTM. We can do, basically the exact same design. And I think that's a great, initial advancement. But then I think thinking about how we say, well, what are we doing? What can we do differently, right? And I think we're just getting to that point in hydrology where we're saying, okay, wow, if we do this 1,000 times faster, all these other things that we've done, because we've had these big models that run really slowly, we don't have to do them anymore. And so we can start to think about, well, what we used to think was a barrier in terms of uncertainty, or a barrier in terms of calibration, or a barrier in terms of, a resolution, or any of these things. We can start to say, well, wait a minute, those don't exist. And so how would we rethink this if we didn't have those barriers in place? And I think that we're just getting there. I mean, it's really in terms of thinking about the sorts of things we can do. But things that were unthinkable, like running an entire IPCC worth of ensemble of simulations and downscaling them and using hydrologic model to look at impacts, that was like, big human need, but that was way out of the scope. That's now completely possible with the models that we have. And so I think there's some really interesting things that this opens up.
So I agree that I think one aspect is to make things larger and faster. So the AI can be used to replace models that we already have, physical models, but were slow and at local scale. So now we can simulate storm surge or compound flooding or hazards at the continental scale, or at the global scale, fast with a lot of emission scenarios and climate change scenarios considered. So that's, I think, one direction and almost like a low-hanging fruit that I think many people are pursuing. The other direction, I think the decision-making part is also quite interesting, that here it's not simply replacing a previous model, but a new idea about incorporating observation, large-scale information into our real-time decision-making or long-term decision-making in a way to adapt to climate change, which is dynamic and very uncertain. So AI can provide us a new framework of doing that we probably couldn't do that before. New ideas of being flexible and adaptive to the future uncertainties.
Okay, so I'm going to ask a question about understanding, but before I ask the question about understanding and interpretability, I'm going to preface it with somewhat of an anecdote. When climate models, which are currently regularly used for understanding and are interpreted, were starting to make their way into the scientific literature, they were criticized for being opaque and not understandable. And that has turned out not to be a first-order impediment. We regularly write papers to understand processes and phenomena using climate models. So things that initially seem opaque may look clear once you turn them around and take the time to understand them. So a question to you, thinking about the various methods that you're using or planning on using, how do you see the tools not just applicable for prediction and describing the world in a better way, but actually for developing understanding of the underlying process and phenomenon and system, the Earth system that we're in? Is it straightforward, or is this really a challenge, the interpretability challenge? We'll start with Reed now.
I thought you might do that. So this is a great question. And I think that interpretability of a whole range of different AI models is a really heated question. And there's a lot of discussion and a lot of discussion that basically leads to, these are black box models, which are really hard to interpret. And then, there's beautiful, Google has a beautiful, demonstration of the weights for, say, an image detection model, which really doesn't tell you, it tells you mathematically where the weights are, but it doesn't actually tell you much about what the model is saying at all. And then I think that thinking about what we've done and to try to grapple with this, we've done a lot of feature importance, a lot of big picture statistical approaches to say, okay, what is the model still from a black box perspective? We sort of do experiments within the, to see what is it relying on? What's statistically the most important or least important? And then we pair that up with the physics. And so we say, okay, well, physics, we know that this should go like that or like that. And how well do these things line up? And try to use that as a way to get at the right answer for the right reasons. But that's still very much an experimental approach. It's very much like tinkering with the model itself. And I think there's a lot to be done to understand really a more elegant way to dive into this. And there's probably people in the room that do this better, but I think that we've got a ways to go. So.
In terms of interpretability, I tend to prefer to think of it less in terms of the neural network is black box, and more as developing methods for explaining, understanding how, say, outputs are related to inputs. What parts of the input explain the prediction that the model made? To me, that's more interpretable than, oh, these weights of the neural networks mean this or they mean that. And there's been a heavy literature in statistics around how to solve that type of question, which is causal inference. And I see that less in the climate modeling, field, but I think that's one framework that has a lot of potential in in developing understanding for climate models, for ones that are hybrid that involve neural networks and everything. There are actually people leveraging neural networks for these causal inference problems. To say that it's less about the black box part, but more about developing a technique that can allow you to answer causal questions. Yeah.
Yeah, so I agree the interpretability is an important aspect. I think sometimes we and students tend to use more complicated models and that we don't quite understand. And this could be dangerous, especially for climate projection, because we don't know, we don't have ground truth to compare with. We're projecting something we don't know. So I think comparing with physical modeling, physical principles is always important. And we can also incorporate future projection based on physics into our training data set to better train the model so that the model is not just rely on the data in the past, which can also be applied for the future. I think you had another question related about.
Well, it's all, is interpretability really an issue? And if it is, what are solutions? But I think you touched on something, Dieng. You mentioned people using more complex models than are needed, and this is not just a feature, a characteristic of people using machine learning, but it's I think it's almost a character of taste or whatever, where there's people who sort of prefer parsimony and others who prefer, in my view, Baroque, or in their probable view, comprehensive descriptions of the system. So are there methods, or is there a philosophy, or is there an approach that sort of enables one to choose what is the level of complexity that is needed for a problem? Or is this one of these, I like vanilla and they like chocolate, and we move on with our lives?
I usually ask my student to use the simplest model, or tell me why it should be more complicated. So I always ask them to develop simple model, then compare to that. Unless it looks, the results is much better, then we should use a simpler model. I think in terms of interpretability, because we understand simpler models than the more complicated model. Another thing now it comes to my mind, you mentioned about using the models to learn about the process, not only just prediction. I think we should do that, and we sometimes do that. For example, if we use the AI to model the storm surge depends on many parameters of the storm. And then once we build the model, we could use the model to tell us which parameters are more important, more in control. So if the storm surge will be higher or lower, if the storm moves faster or slower in different geometric places, and actually that was very helpful on that.
So looking at the time, so there's time so eventually we're going to go to audience questions, but one of the things, and I see Alistair there, Alistair Adcroft, and I remember, one of the standard things when you develop a dynamical model, there are certain solutions to the system that you know ahead of time. You do with an ocean model, you'll do maybe a soliton test where you put a little hump and see how it propagates, and you have an analytic solution, and you know what the solution should be in a general sense, and that gives you, a test of your model. Mm-hmm. Are there equivalent types of tests that we should be doing, or are the systems that we're modeling so unknown that we are left with no purely theoretical test cases? I'm thinking for the materials, or for hydrology. To me, hydrology is opaque, right? Especially below ground.
For materials, you can always, if you're working with experimentalists, you can always try to make things in the lab and study stability and synthesizability. Or you have these techniques that are derived from theory, like density functional theory, that's still also an approximation to the Schrödinger equation. So it still is, even if it's based on theory, it's still an approximation. due to a trade-off between computation and accuracy, and that's what everyone is using as a ground truth for evaluating these machine learning for materials algorithms and models. But yeah, I think if there's a theory out there that says what truth should be, then figuring out a way to scale up that theoretical model as a way to do testing faster is a good way to go. DFT is one example of that, like approximating what solutions should look like so that you can evaluate faster. Yeah.
So in terms of hydrology, I think there's a few pieces to it. And one, to get to your a part of your prior question, a lot of the complexity for me is around the connections. And so, so many things are interconnected, so many things are nonlinear, and those are the more important interactions to capture with a model. And sometimes those connections and the model's ability to capture those connections are more important, those interactions are more important than whether or not it gets sort of like the right answer. Meaning, if you say, well, the water table depth is X here, and the model has some error on that, but then the model captures these relationships between groundwater pumping, irrigation, feedbacks to boundary layer and climate, that's more important. Those feedbacks are more important in terms of the physical connections. And so in terms of sort of the tests and things, we have a number of similar kinds of time for us to be done. So similar types of unit tests or analytical solutions and things that we use for our models. But then also, this is why we, millions of data points, right? Because the subsurface is super opaque. It's opaque to me too. It's out of sight, out of mind, and so we have to build these big databases, these comprehensive databases, to use the data to really evaluate these models, because they're so hard to evaluate in other ways, and there's not a remote sensing product, there's not a national network, there's not other things that we can use, and so we sort of have to build these from the ground up to check both the AI and machine learning driven approaches and the physics-based models.
All right, so I'm going to close my final question to you. And preface is, in my view, there are two types of technologies. There's dishwashers and there's email. And the difference between those two is dishwashers, at least to me, when we started having a dishwasher in my household, it freed us up to do more with our time, do different things. We could read more, we could spend time with each other talking. And so it enhanced the overall intellectual and sort of productivity of ourselves. Email, in my experience, and I think experience of most of us here, has been the opposite. It's a technology that initially replaced something, yes, the memorandum, the phone call, and then it overwhelmed our time.
Yes.
We have now less free time than we otherwise would because of email. With these technologies, how do we work so that they are more like dishwashers and less like email? Is there safeguards that we could put into ourselves? Any thoughts?
I think the hybrid approach is trying to make these AI models more reliable when it comes to climate and also physics modeling-based approaches. And people have been doing that in different ways, trying to build architectures that are aware of the physics, or so as to constrain the model to not deviate too much from the physical laws. Or you can embed these physical constraints in the objective function, trying to achieve the same thing. Or you can start with the physical system itself and try to predict its parameters using AI approaches. So people have been trying to make these systems more useful and more faithful to the underlying physics, to be more like dishwashers. Yeah.
So, I mean, there's a quote that I've seen a million times online, which is, AI can write it can write for us, it can make pictures for us, so that we have more time to do other stuff like clean our house and do laundry, right? But what we all want is we want AI to clean our house and do laundry so that we have more time to do the fun stuff like writing and making pictures and making art. So I think this is tricky, right? Because I think it's really easy for it to take the creative part, the physics intuition part out of the equation. And then what are we doing? We're just moving data around and feeding it into a big algorithm, as opposed to being able to find the way that we still have the time to have the intuition to think about the processes, to think about the big problems.
I think for us, from an application perspective, I don't want to make things more complicated. So I would want us and the student to start from our fundamental problems to solve the decision-making problem, predictive hurricanes, and so on, have the ideas what we want to do. And then maybe we'll use AI as tool to help us, rather than saying, we're going to use AI, we learn a lot of AI, we have to use AI. So sometimes has to be remembered to AI are tools that we may use in solving problems, helping us, rather than we have to use it. That will be a burden.
All right, thank you. So now we move to the audience participation part of the dance. I see a hand there, and there are two proximate to each other, so that's efficient. So let's start here.
All right, it's dangerous to let me ask a question, but my name is Ron Beck from Aspen Tech. So you were dancing around a lot of interesting questions about using the AI to educate the students versus, educating the world, if you will. But I see one of the discontinuities between students coming out of school and then being, let's say, excelling or useful in business or a technology context. To me, one of the biggest issues is the best students come and then they're great at working by themselves, but they don't necessarily know how to work in teams. And business or technology companies they're all about teams. And so I think this, the hybrid topic that I don't know how you say it, Adji?
Yeah.
Yeah, so that she keeps going back to is, this hybrid idea. And I think we see the same thing. Our company builds hybrid models, and we are challenged to get people to adopt them. And it turns out the trick is you have to team people who are good at data science with people who are good at the domain. Because you can't really, like you said, you don't have time to educate everybody on everything. So you actually need people who know the different topics. But, any thoughts on that as to how you do that? Because I think, Princeton, I went there. So, it's great at teaching you to work by yourself, but it doesn't actually have a lot of things that involve teams.
So how do we train more forest people to work with tree people?
I love that question, because in setting up my lab, that was the biggest hurdle in trying to work multidisciplinary. That involves having students who can actually do projects that can tackle challenges in these fields. And the approach that I've found to work is to find very good resources in the areas we're interested in, and initially collaborate with domain scientists. And when collaborating with domain scientists, to make it clear that our goal is not just to deal with the data, that we want to understand the problem at hand, and we want to understand the science behind, and we also, so that they can teach us the science and we teach them the data science part. So we all end up out, when we finish the project, with augmented knowledge in addition to solving the problem. So they get to know more about machine learning, and we get to know more about the sciences. And we've been doing that in different areas. In chemistry, now we can run molecular simulations. We didn't know how to do that before. In material science, the same. We've been looking at quantum physics, and that's just from that approach of not fearing learning about a domain, because the assumption is that we have the fundamentals, so we can go and invest time in learning a little bit more and discussing carefully with domain scientists, and then go from there. Yeah, that's the approach that I really enjoy, actually. Yeah.
So I'll yes and Adji's great answer. We've tried to do this in my group as well, and we have research software engineers. We have a real diversity of different skills, and we also collaborate pretty broadly. We collaborate with faculty in astrophysics. We collaborate with faculty all over the U.S., and it's real tight collaborations, not just sort of working on two pieces of a project that are supposed to get, hooked together in the end, but like really more in that team's mode. Because you're right? And if you think about the grad school or the postdoc level, it's twice removed that somebody is really good at working alone on things, and then that gets them into a good grad school, and then they're even better at working alone on things, and then that gets them a good postdoc, and then all of a sudden they're out in the real world and like everything is flipped. And so you have to provide this experience along the way so that they understand how to do this much earlier on.
Just want to mention that Princeton is really good at interdisciplinary education and research, even before we talk about AI. Myself has background in engineering, mathematical science, and climate science, and also policy. And so I saw myself best fit in Princeton from 12 years ago. And now with AI search, I think this is more important to be able to be open-minded and work with people in different disciplines. And that's principle in Princeton.
Okay, so 1, 2.
Yes, this is a little off in the left field, but it seems to me that the 800-pound gorilla in this is that there's a large part of the public who just don't believe any of this. And they really don't want to hear from educated academic elites about this issue. And this is a real problem to solving the climate problem, because it involves laws being passed that you can't even talk about climate problems in some states. So what can we do, or as academic leaders, what can you do to reach some of these people? And I know it's very difficult, but some ideas?
So in 15 seconds, I can solve this. No. This is, you've touched on a real fundamental challenge where, because climate and energy involve sort of demand political decisions, the underlying information that makes us aware of the climate and energy connection and the challenges in climate and to running energy are treated as political aspects, when in reality they're not. They're just policy relevant information. So how do we communicate that better? And I'll let the panelists answer, but I'll give you my philosophy on it. And it's to be as much as possible perceived as impartial, perceived as not having a pony in a race and not being an advocate. Now that is a challenge, because if people advocate at you, how do you play the honest broker while not seeming as an advocate? And I don't know, that's a challenge. The other one is we need to break out of our little ivory tower. We need to have different friends sometimes. I don't know, other thoughts?
I'll jump in on this. So this is one of the reasons we got into machine learning, because while people may not believe that there's climate change, they live in a world where there's less water. They live in the world where there's more frequent droughts, there's more frequent wildfires, there's more frequent floods. Like, all of these things are happening. And water managers and decision makers need information to make better decisions. And this wasn't touched on much. Ning kind of hit this a little bit, but I think it's really important to note that, like, you don't see many straight machine learning applications that are data-driven in the climate sphere being good at climate projections, because they're off their roadmap. So machine learning approaches are really good. They're really good interpolators. They're not great extrapolators. And so one of the challenges is that you need domain discipline, you need expertise, you need models, you need the understanding of the physics to say, okay, this is why it's going to get drier, and this is how, this is information that's going to be helpful to a water manager or somebody who's pulling levers on a dam in the upper Colorado. But they're not going to wait for, a 500,000 CPU hour simulation to finish to get their answer. They want something. They don't actually care if it's super, super accurate. They want something. They're fine with something that's statistical, but they want something that they can say, all right, I want to do 10 scenarios, and I want to do this and this and this, and then, oh, okay, I want to do 5 more, and I want to do this, and I want it to happen all very quickly. And we did a lot of work in my group working with decision makers in a whole bunch of Western states in the US. And that's what they wanted, and that's what sort of drove us to these machine learning emulators that would give them these robust but sort of fast and almost accurate answers that were useful. And so, I mean, it's a counterpoint to Gabe's great answer, but it's also that, these things are happening, and it's not, all of the water, all of those billion-dollar weather and climate disasters that I showed in that first slide, they're there and everybody's living in them. And people need information about how they're going to happen, where they're going to happen, and how to adapt.
Maybe there's a need for more climate education, because maybe they cannot explain these natural phenomena that are happening. They cannot tie it to climate or how it's caused by climate. And so maybe putting educational resources out there. I'm being naive, but yeah, maybe that can help.
So there, and then we...
Hi, Martin Franzen from Mercator. I was wondering, so last year, August, September, October, we saw record-breaking temperatures, but not just record-breaking temperatures. And there are some prominent people in your field that have basically interpreted this as the distributions have basically shifted. The attractor is moving. We're now entering a new regime. And given that so much of the base models are heuristical, based on empirical data, how do you see going forward training AI on data that may be belonging to a different regime?
So I think that's a fundamental question, right? And some of the physics-based AI may help us over that hurdle.
Yeah.
But
that's when I said that, you don't see a lot of data-driven approaches being able to extrapolate out under climate scenarios. It's exactly that. So we have non-stationary signals, so the statistics are not stable over time. And Dieng has also done a lot of work on this. And I'm sorry, we didn't get to answer the last time around, so I'll be quick. But this is one of the reasons that we use models, because we're able to generate these. We're training the AIs not necessarily on data, but on model results for climate perturbations, so that they can understand what that looks like in that space. Otherwise, we haven't found them to be particularly good predictors of climate-type scenarios if they don't have that in their training.
Yes, that's the fundamental limitations of AI, is that it cannot generalize out of distribution. People are still grappling in the field about how to do that. In the space of AI for materials, we found that even these benchmarks that people have put out in trying to build models that can generalize out of distribution, it turns out actually the representations that these models are learning that in the test data are in distribution. So they're not really actually performing well out of distribution. And so this is a very big challenge in the field. We don't know how to deal with it.
I was just mentioning that when we train these models, we need to be super careful and hopefully involve the physical part, and parameters has to be covered so that we're not doing extrapolation. Another point I think is we can try to use machine learning and physics model and the data all together and try to use the maximum data. For example, tropical cyclones, we have limited data of past few decades, but people have been developing paleo records. So in the ancient times, when storm surge comes, they would deposit these sediments into inland regions. And now if we can take out the core, we can date back, look at the sediments. We can recover thousands of years of historical records of the tropical cyclones. So those kind of information can help us to look at the longer prediction in the future that we don't know.
So we have time. I was told we have time for one question. I think that was the first hand I saw, or no, the most recent, the gentleman standing up, right? Yeah.
Just was a very short comment on the notion that we need more climate education. I agree, but it only would solve part of the problem. There's a whole community out there that not only rejects that humans cause climate change, they even reject that there is global warming, and they make up all kinds of reasons why the measured increase of temperatures is just not true. They even reject the notion that we can determine an average temperature. So what to do there?
So, I mean, my answer to that would simply be, you might not care about climate change, but also climate change doesn't care what you care about. So maybe we have time for one question. I saw in white in the back with the long hair. I can't see very well.
Hello, hi. Oh, God, sorry, that's loud. You had talked about being impartial, and I think being impartial specifically when you're producing data is very important. So I was wondering, as the head of Meadows, do you see a problem with the fact that BP, the fossil fuel company that is funding CMI, has just rolled back its climate commitments for more oil and gas extraction?
Do I see a problem with that? I mean, I see BP as having made a business decision. I don't see BP as having had programmatic influence based on that decision and the science done. Were I to have seen evidence that BP has had that decision sort of feed into what gets published and what doesn't get published, that would be problematic. I think it's important that people publish their results and do the science as impartially as possible. I think that is sort of basic scientific ethics, and so that's what people should be doing.
Can I ask a follow-up? It's okay if not. I was just going to ask what kind of measures you put in place to make sure that BP's business decisions don't influence the research that you're producing, such as not committing to.
Yeah, I mean, we can have a longer discussion on this topic later, but I think the leadership at CMI makes the decisions about what research is supported, and it is not a decision directly by BP. That's been documented and made very clearly. If anyone has any questions, the leadership of CMI is Steve Bacala and Jonathan Levin and Amilcar de Porporata, and you can talk to them. Much like any other research project, the PIs make the ultimate decision on how the science is done, whether it's supported by a foundation, whether it's supported by industry, whether it's supported by government foundation. And much in the same way that when we have one administration in the White House or another administration in the White House, it does not affect the research that comes out when it's federally funded.
Okay, so we have to call it in. Thank you, Gabby, and all the speakers. I really love the dishwasher email analogy. It's wonderful.
So and Rob, I don't know if you want to give a correction on or an addition on that, because. Not a correction, but I'm happy to talk to you. Oh, yeah, Rob Sokolow is here as well. And so just as a summary, climate is a great challenge for society and for how to live and produce energy. I think, thank you to Adlinger for having us here, and look forward to further discussions.
Absolutely. So it has been a long day, and we have went through many topics, all the way from computing to power for AI and AI for power, and finally AI for climate. And we learned a lot, and at least for me, I have enough data to train my brain, and then really digest all the information that we want to improve our understanding. So I'm not sure if we'll find enough energy to power AI. I'm not sure how much benefit AI will really bring to help us make the world more sustainable. But I know as human beings, we need more intelligence. We need more energy. We need more sustainability. So this conversation will keep going, and we're just at the start. So we'll wrap the sessions for today now. But before that, I want to thank a few important people that make this event possible. One is Professor Barry Rand and Dr. Chris Craig for developing and organize this annual meeting. And all of our moderators and speakers, who many of them have traveled around the country or maybe come from overseas, and they really bring all the insights to Princeton and make this event possible. Thanks all. And finally, and most importantly, all the staff members who have been working tirelessly over the past few months and taking care of all the details from events organization, logistics, traveling, everything. Specifically, I want to call Diana, who is right there, Vivian, who worked closely with us to put all the contents together. Dieng, who's managing, sort of overseeing everything, and Ashley and Bumper and many else. I couldn't call the numbers. Probably some of them are still outside. So that's the end of today. And we will have a refreshment session and poster award session outside, so you can go out. And then also, if you want to talk to the speakers, you can stay here a little bit. Thanks.